Good evening, good afternoon, or good morning, wherever you're at. We're going to be looking today. I'm going to make a video about errors in chemical analysis. So it'll be in three parts, so it doesn't get very boring and overwhelming with information at the beginning. We're going to look at controlling errors in both quantitative and qualitative analytical chemistry or any measurement involving chemical processes. So the role of analytical chemistry in science is huge. It's very underestimated. I mean, we need to know test results to do just about anything, even something like pouring concrete. If you're going to be doing a big, huge job, you want to make sure that you're analyzing it and making sure that you're getting the best of the best. Without accurate and precise measurements, we're left with very small legs to stand on. So we need good information. Analytical chemists play a vital role in almost all the major scientific projects. At some point, something's going to get sent to the lab for analysis. And the analytical chemists can provide vital quantitative and qualitative information. And you all probably understand the difference between quantitative and qualitative. Qualitative is just more of a presence or absence type testing, where quantitative is where you are actually measuring and quantifying something. By the way, I'm basing a lot of my presentation off of Skoog, Holler, and West. They wrote a very good book on analytical chemistry. So if you're looking for a good book in analytical chemistry, Skoog, Holler, and West, 7th edition, very good book. And the beginning is all about statistics, and it makes a lot of sense once it's laid out that statistics very well before you start getting into analytical chemistry. So the steps in a quantitative analysis is you're going to select your method, obtain a representative sample, prepare a lab sample, getting rid of interference compounds. You might have to melt something down. You might have to evaporate something away. There's a million different ways that you could prep or have to prep a sample in the laboratory. And then you're going to prepare replicate samples because you're not going to run just one. You're going to run more than one. Always going to run more than one sample in case something goes wrong. And you also like to have statistical information to show you how good your analysis was. You get samples the proper phase. Does it need to be you have a solid that you need to dissolve into a liquid, or vice versa? Do you need to evaporate liquids away? So there's a lot of things that you might need to do to prep your sample, including eliminating all interferences. So to measure the property of the analyte you're looking for, the pH, titration endpoint, retention time on if you're doing chromatography, you calculate the results, and then you want to estimate the reliability of your results. So we always want to be looking at how reliable are our results. Just because we think we measured something, that doesn't always mean that we have. You'd be surprised. Getting the proper sample. If the sample is not homogeneous and it's large, a representative sample can be difficult. You might need to use statistical methods to get a sample that's representative of the total mass that you're trying to analyze. The chemist's analysis is only as good as the nature of the sample submitted. So, if a bad sample comes in the lab, the analytical chemist can't do much with it. There's statistical tools that can be used to ensure the sample is appropriate. You can use statistical methods to say, hey, it's a big, huge sample, but I took, a lot of people use the square root of n plus 1 as a guideline as to how many samples you should be taking of something, because even in a process in a factory, you're going to get drums of raw material in, and they all may be the same lot, but you're going to get 15, 8. I've seen pallet after pallet. I've seen 80 drums come in that are all the same lot. How many should you sample? Well, we used to use pretty much the square root of n plus 1 But there are better tools to get it down even more appropriate and drill it down so that you got a very representative sample. Replicate samples should be carried through any analysis to increase the validity of your test results. And of course, you always want to be thinking about interference elimination. If you have a compound that's very similar to the one that you're analyzing, like a side product, an unreacted side product, it can be difficult sometimes to separate what you're trying to measure out from that. So we'll talk about that later on. Calibration and measurement. Calibration is huge. All results depend on a final measurement of X of a physical property of the analyte. So you got to be measuring something like you're measuring a specific bond, chemical bond, or a series of chemical bonds, or in chromatography, a retention time. How long is your sample staying stuck to the column that you're running it past? That goes for GC and HPLC. There has to be a relationship between the quantity of the analyte and the signal used as a determinant. So, like with a basic HPLC, for example, you'll have a UV detector. So you need to be able to draw a relationship between, say, the double bond absorbs at a specific wavelength. So you need to have that relationship between what what you're measuring, and it has to cause a response in the instrument or the individual. Sometimes individuals are running these tests. We call that wet chemistry when you're doing it at the bench, and you have titration methods that you use. Uh, Concentration of the analyte should equal a constant times the unknown. So you don't know what that constant is. This is just a very basic equation to try and say, you know, you need a constant times your analyte to get a signal. So again, very simple stuff here. We'll get into more define things later on as we. This is just very elementary to begin with. It's impossible to conduct a chemical analysis without there being some error introduced. You're always going to have some error. Even if you got everything perfect, you still have the Heisenberg uncertainty principle that the measurement itself is disturbing the actual sample in some way. So there's no such thing as a perfect analysis. There's always some level of error. Running multiple replicates through an analysis is a good way of controlling for those errors. So you have more than just one sample. Taking the mean of multiple replicates helps to smooth out the data. Real quick, talk about the mean versus the median. The mean, of course, is the average of the data. The median is the middle of the data set, and you arrange the data set in order of magnitude, and you pick the one that's in the middle. Uh, why bother? Why would you bother doing that when the average seems to be much more useful? It's good if you have an outlier. So if you lay the data out in terms of magnitude and you have everything's pretty much like close to the number 10, and all of a sudden you have a sample that's 25, it's evidence that you might have an outlier. So it's good to keep median in the back of your head as something that can be useful. The median, as we just said, is helpful if you have an outlier. The mean, again, simply the sum of all the values divided by the total number of values. The median is in the middle of the entire data set. If that data set is an odd number, the average of the two in the middle is the median. So if you have an even set of samples, you can pick one in the middle. If you have an odd set of samples, you can average the two that are in the middle to get your median. Important terms. Sorry about that. I need my coffee. It's kind of early here in the morning. Important terms in chemical measurements. Precision. Precision describes the reproducibility of the measurements. It's the closeness of the data to any replicates that you may have brought through the analysis. So it's the closest of the data. Terms to define precision are going to be things like standard deviation, variance, coefficient of variance. We'll touch on what each one of them mean in the three videos I'm going to make on this subject. These are all a function of deviation from the mean. Accuracy. Accuracy is different than precision. Accuracy is the closest to a test result when you already know the result, right? This can be used to test the method that you're using. It should be accurate you when you test well-known standards with known values. So you'd have NIST or USP grade if you're in the pharmaceutical industry. Those grade standards, and then you would prepare a sample the same way you're preparing your samples, carry it through, and it should give you the same not exact, but close to the same result. So you should always be looking at the accuracy of your method. Things can drift. Your instrument can drift. So it's not a bad idea to carry one of these samples through every analysis that you do if it's data that's extremely important, like pharmaceuticals. And you have the absolute error. Okay, this is the level your test results drift from the established reference standards. Again, a real simple equation there. Absolute error should be either positive or negative. So you're either going to be high or low. You can have a negative reading for accuracy. It means you were just below the accepted reference standard. Relative error, real simple. It's the absolute error from your measurements divided by the true value. It's expressed as a percent. You can transform that into parts per million. Why is that important? It gives you a percentage, right? So you could have an absolute error of 6. What does that really mean? Well, put it into relative terms, you might get a 16%. Well, that's big. That's huge. If you're dealing with a larger data set, and you're 16, and you know it's not as big of a deal. If it's say 2% or 3%, that's one thing. But if you're at 16 or 17%, you might have yourself a problem. So relative error is something to keep an eye on. You should always calculate your absolute error into relative error. Types of errors in chemical tests. Well, you have random errors, indeterminate errors that affect precision in your data. This could be electronic noise in the instrument you're using, errors caused by humans, reading of a meniscus. A lot of people still struggle with reading that meniscus perfectly, and it could matter depending on the titration that you're doing. Pipetting errors, not every human being pipettes exactly the same way. There could be a little bit of error introduced there, and even data transcription errors may fit into this category. People may make errors when they write down results. It happens. We see it happen all the time. So these are types of errors you got to keep an eye on. Systemic or determinate errors. Okay, this is a drift that applies to all results. Everything is affected by a systemic error. The instrument is broke in a way that it affects every single sample. It's a drift that applies to all results. So an auto sampler, for example, an auto sampler device has fallen out of calibration. You don't know it, and it's adding a slightly higher amount of sample, loading it onto a chromatography column, and you're not aware of it. Well, this is an error that's going to affect every single sample. Accuracy is affected, uh, but by the same amount to each replicate sample. So again, it's going to affect everything, carry through your analysis the whole way. It's easy to makes it easier to identify and correct for because you have a set value that everything was off by. If everything was off by 3%, well, you could correct your data depending on what you're doing. In the pharmaceutical industry, that wouldn't be allowed. But in some labs, if you see that you have an error, a systemic error, you might be able to say, hey, this threw all our test results by 3 or 4%. Let's just subtract the 3 or 4% off each one. Some labs, you might be able to do that. I'm not sure about environmental labs. I know it wouldn't fly in the pharmaceutical industry. But if you're doing other types of work, academic work, you might be able to do that as long as you're sure of the error. And then you always have outliers. Not always. I'm sorry. Let me take that back. there could be outliers, and outliers are easily identified as they're far away in value from the other replicates in the data set. They're way adrift. Outliers are usually caused by some type of a gross error, like an instrument failure, or an individual making a serious error, like they double diluted or added way too much of the standard, or they, when they were adding the sample, they made it some type of gross error that caused it to be off by a lot. Sources of outliers should be investigated and not removed from the data set until a full investigation reveals what caused the outlier, and a corrective measure should be devised to ensure it won't be repeated. In the pharmaceutical industry, this is certainly the case. If you have an error like this, you're going to open what's called an OOS, or an out of specification investigation, where you're going to investigate what might have happened to cause this outlier. And then you're going to come up with a CAPA, a corrective and preventative action. And you're not going to move forward in most cases until you do this. You identify what caused the problem, and you make sure that it won't be repeated on future samples. And that all gets documented. Effects of systemic errors on analytical test results, again, they're either constant or proportional, right? A constant error, these are independent of the size of the sample. For example, the concentration of a solution is the same. So if too much is added to all the replicates, the sample error will be the same in each. Proportional errors, here you have an error where in one case it will be larger or smaller according to the size of the sample. This happens like a lot with interference. If you're running a very small amount, you might not be affected by the interference, but as you get larger sample sizes, the interference may become much more of a problem. So you either have constant or proportional errors. Again, proportional errors are when the bigger your sample, or whatever it is that you're doing, you've got an error that's additive, that's going to be of more significance, where a constant error is just the same all the way through. Detection of systemic errors, instrumental and personal errors. Calibration is the best way to detect systemic instrumental errors. So calibrate your instruments every day, every time you use them in most cases. Standard reference materials should always be employed to ensure that instruments are working properly and producing accurate and precise results. Certain industries demand frequent calibration. Again, the pharmaceutical industry, which is where I mostly come from, for most purposes, they want you calibrated on each unique assay you're doing for a drug product, and they want you to use a USP reference material. And there's a whole process called method validation that I'll get into on another video one day. And accuracy and precision are two things you have to address when you're validating your method. You're not allowed to use your analytical method until it is validated. And you have to do that in most cases by purchasing USP reference samples and making sure that your assay, the one that you designed, can measure that particular analyte. And now they've more recently the USP started to give you that reference sample and a very closely related sample to make sure that your method is good and precise and accurate, and that it can separate the two compounds that are closely together in structure. So it'll send you sort of a challenge to see how good is your assay. Can your chromatography separate these two closely related samples? And then blank determination. This is something, again, a blank solution can be made up with all reagents minus the analyte in question, and the blank can be run to reveal any interfering compound. So when you run the blank, you kind of get a signal with nothing in it. The signal generated by the blank could be used as a correction to apply to the replicate samples of a result of an analyte. Again, this would never fly in the pharmaceutical industry. What I'm saying here is that you suspect that the instrument is off by about 3%. you make up a sample with none of the analyte you're trying to analyze, just a blank, the reagents, what it's dissolved in, and whatever buffers or anything you're using, and you run that through and you get your signal. And we'll get into signal and to noise ratio at one point down the line too. But you can use that and say, hey, here, look, we are off by 3%. This method is effective sometimes, but it's not acceptable in critical applications, especially pharmaceuticals. The method there should be a thorough investigation anytime something fails or there's an outlier of any sort. Uh, so, coming up next, we're going to look at random errors in analysis. This will be, again, another shorter presentation and cover some of the types of errors you might see in analyzing chemical data. The next presentation will cover these random errors. These are things that you just can't control. They're errors that arise when a method or instrument is pushed to its maximum sensitivity. So you're pushing that instrument out to its maximum sensitivity on the low end or the high end. And understanding random errors helps set the foundation for understanding the limits of the method you're going to use. And it's vital in areas like pharmaceuticals and situations where the measurement must be, as I said, validated, right? So we want things to be always as solid as possible. And that's it for today, guys. Thank you very much. We will be back with another video shortly. Take care. Bye.